Okay, the last thing we want to talk about today is property approximations. Certain times we can't look up the properties exactly in the tables. And I've talked to you about this already in a previous lecture, but I'm going to mention one of the property approximations that we're going to deal with is going to be the liquid approximation. I'm going to list it here. And the reason why we have that, just to refresh our memory, is because only water has the compressed liquid tables. Everything else doesn't have compressed liquid tables, so how do we find the properties? We look at those and say, well, the specific volume at some temperature and pressure is approximately equal to the specific volume of the saturated liquid at the temperature at which I've been given. And the internal energy at some temperature and pressure is approximately equal to the internal energy of the saturated liquid at the temperature I've been given. And I think it's very important that you have to understand that it's the temperature that we look up the specific volume and the internal energy of the saturated liquid. Do not look it up at the pressure. It is not something that is a function of pressure. You'll be significantly off, and sometimes you'll be lured into believing that that's where you need to find that property. But it's on your equation sheet. Don't make this mistake. Okay, don't make this mistake. It's only similar when we're looking at the temperature side of things. Now let's talk about enthalpy here. Enthalpy, we said enthalpy as a function of temperature and pressure. Remember, those are the two things that we're looking these things up. We're not saying times temperature and pressure. We're saying as a function of temperature and pressure is approximately equal to, then, if we did a liquid approximation, the internal energy of the saturated liquid at some temperature plus pressure times the specific volume of a saturated liquid at that same temperature. Okay, so we'd have to look up and calculate what the enthalpy is. However, or we can also say that the enthalpy of a temperature and pressure is approximately equal to the enthalpy of a substance at the saturated liquid, looking at it up at the temperature, plus VF, looking up at the temperature, times P minus P saturation at some temperature. This is another way to look at it. If you don't want to look up and say, okay, let's look at the definition of enthalpy as U plus PV, and we say, okay, I want to look it up in terms of enthalpy, we have to add this term here. Okay? Now let me tell you about this term. You'll see this on the equation sheet, and I have a double underline of this, because this helps correct this enthalpy of saturated liquid at low to moderate temperatures. It does not help us a lot at moderate to high temperatures. And what we're going to be dealing with in Thermo 1 is a lot of moderate to high temperatures. So basically what you're going to be able to use is this equation, just like you did everything else, that the enthalpy at some temperature and pressure is approximately equal to the enthalpy of the saturated liquid at the temperature that you've been given, just like you did up here with specific volume and internal energy. I have to show you that this is over here is something that you might be considered about when you're dealing with very low pressures and temperatures. And I will tell you, if you need to use that in this class, you're just not going to need it in this class. In Thermo 2, you might need to use that correction term to help you correct it from using this value. Okay, so that is the liquid approximation. The second type of approximation we're going to use is something called the incompressible substance model. Okay, what is an incompressible substance? Well, incompressible substances can be something such as a solid. Okay, a solid is obviously something we're going to look at, and we're going to say it's basically incompressible. In the situations, in the pressures that we're going to use, and the temperatures that we're going to use, we're not going to be able to compress copper, steel, those kind of things. So incompressible substance model will apply there. But also we can deal with liquids. Water, for example. Water is basically an incompressible substance. Its bulk modulus is in the gigapascals when you're looking at it. So it's why we have the water hammer effect that comes in your pipes. That's something you'll deal with in fluids. So if something in this class is a solid, or something in this class is a liquid, and it's liquid in all cases, we can consider it to be incompressible. And so if a substance is incompressible, what has happened there? We can say that dV, the change in volume, is equal to 0. The change in volume is equal to 0. Okay, so here's what I want you to do. Let's recall something we talked about earlier today. Recall that C sub V is equal to du all over dt. Now look what I've done here. I've changed the integral from I changed the derivative to an ordinary derivative from that partial derivative, because now we're only varying with respect to t. We're not holding that. We're not looking at that volume, because volume is not part of the situation. Volume it's incompressible. We're not worrying about it. Okay, and we know that enthalpy as a function of temperature and pressure is equal to the internal energy at the temperature that we will be given plus PV. Okay, now PV is going to be constant at some pressure. Okay, if pressure is constant, we can have a situation where this is going to be equal to, this is constant. This is constant because the volume is just not changing. Pressure is constant. This whole term is constant. Volume is not going to change. Okay, so let's take this and let's take this equation. Let's differentiate with respect to temperature. And what we're going to get here is we're going to get the partial derivative of enthalpy with respect to temperature, considering keeping pressure constant, because it's now a function of two things. So we're going to take the derivative of enthalpy with respect to temperature, keeping pressure constant, is equal to, on this side we have du, or I should say it's only a function of one thing, so it's the ordinary derivative, du over dt. What is this? We're saying that specific heat at constant pressure is equal to the specific heat at constant volume. And that should make some sense to you. And when you're dealing with an incompressible substance, the energy required to raise the temperature of that incompressible substance 1 degree is going to be the same in constant pressure, in constant volume situations, because the volume is not going to change. And so the only thing that can happen is the pressure is going to be constant there as well. So the pressure C sub P should equal C sub B. It just should make logical sense there when you think through it. And so we don't even determine it. We don't even say C sub P or C sub B. We just say C in our calculations. We just say C. And it's constant over a limited range of temperatures. So C is constant of temps. Okay, so we're going to say this. C is equal to du over dt, and we can separate variables here and say that du is equal to C times dt, and we're going to integrate this between 1 and 2 and 1 and 2, and we're going to use the fact that specific heat C is constant over a range of temperatures, and we're going to move that C outside of this equation and get that u2 minus u1 is equal to, this is constant, C comes out of the integral, times T2 minus T1. Okay, so this is the incompressible substance model. The incompressible substance model says when we have an incompressible substance, we can replace u2 minus u1 with specific heat times T2 minus T1. And it doesn't matter which specific heat we look up, C sub P or C sub B, they're the same things. And so what often you're going to be in the tables, you're going to look up C sub P. That's what they're going to give to you. So C sub P, you're going to plug in here and say, hey, I don't know what the change of internal energy is. I don't have tables in the back of my book for iron or aluminum or copper. I can't look up the internal energies in these cases. What do? Well, I just look up the specific heat, take it times the delta T, and that approximates what the change of internal energy is. Importantly, I can do this with water. If water is a liquid in state 1 and state 2, I could look up the things in my tables. I could look at the compressed liquid tables. I could do the liquid approximation for state 1 and state 2. Or I could look up the specific heat and say, okay, specific heat times temperature 2 minus temperature 1 is going to approximate what we are looking for the internal energy change. Okay, now let's see what would happen if we did enthalpy. So the enthalpy, H2 minus H1, is going to be equal to the integral from T1 to T2 of du, which would be C times dt, plus specific volume times P1 of P2 of dP. So remember, this is going to be here, this is basically U plus PV. U plus PV. And so here's U. U is up here. Here is PV. And remember, volume is constant, so that comes out here. Just waving my hands over this a little quickly, so because we're getting to the end of the lecture. Okay. What is this going to equal? Well, this is going to be equal to enthalpy 2 minus enthalpy 1 is going to be equal to specific heat times T2 minus T1 plus the specific volume times P2 minus P1. And what's going to happen is this term here is very often small and can be ignored. Okay, and so often what happens here is we're just going to look at this part of the equation and we're going to say that delta H is equal to delta U when it comes to incompressible substances. That's what we're going to cover. It's all going to boil down to this. So the main thing that you need to understand here is when you're dealing with a solid and you have to find its internal energy change or its enthalpy change, we don't have tables for it. We just don't. We're just not making up all these tables because this approximation, this incompressible substance model, is pretty darn good. And that was what we'll use to set our states. Okay, with that, I think we have enough information to keep us going and to get us through the day. And you should be happy and have lots of other information to solve lots more problems that we can work on. And we'll go with that and end this lecture.